Well, we've learned that torques allow objects to experience angular acceleration, or in other words, causing their rotation rates to speed up or slow down. There's actually vastly more situations when torques are present and no rotation even occurs. And these are examples known as rotational equilibrium. And we're actually going to see that studying this particular type of setup is going to be very, very useful because it actually allows us to solve problems where there's no rotation at all. So we learned a long time ago when we were discussing forces that if we consider an object to be in equilibrium, that the forces on this object are balanced, and therefore that the net force is zero, and that the motion of the object will remain constant. It's not going to accelerate or speed up, slow down, change direction, etc. It's just going to maintain its current constant velocity. But the thing is, though, is if we reposition these forces, the forces on this object are still balanced. We still have a force up and a force down. But no longer is this object going to be completely motionless because the torque on this object is not zero, the net torque. In fact, it's going to start rotating in the clockwise direction. So now we need to add in a second statement when we're talking about objects in true equilibrium. Not only do the forces on the object need to be balanced, but to have proper rotational equilibrium, we're going to have to move the forces so that the torques are balanced too. So if an object is in rotational equilibrium, the torques on the object are balanced and its rotational motion will remain constant. So it does not angularly accelerate. It's going to maintain whatever its current angular velocity is. If it's not rotating, it will continue to not rotate. If it's rotating at some constant angular velocity, it's going to continue rotating at that constant angular velocity. But there's also a little bit of a trick to this. So let's go ahead and look at this as like a sword display case, some sort of sword rack that could be on someone's wall. This was particularly a military sword. And if I'm going to go ahead and redraw this sword here, and I'm going to draw an FBD for it, well, we're going to see that on this sword there are three different forces, and obviously the net force has to be zero because the sword is not accelerating around, it's just sitting there at rest. But we have the force due to gravity at the center of mass of the sword. We have F1 and F2 from these two different little hooks holding it in place. And the thing is, though, is that it's also not rotating, and it's not starting to rotate, so the net torque on the sword must be zero. But if the net torque is zero, well, what is the axis of rotation that we're considering here? Well, let's go ahead and say maybe the axis of rotation is the center of the sword. And if it's the center of the sword, that means that, well, we've got the torque due to gravity going this way in the counterclockwise direction, and the torque from F2 also going counterclockwise, and those must be balanced by the torque from F1 going clockwise in order to keep the net torque zero and to keep it motionless. But how do we know that's necessarily the right axis point? Instead, why couldn't I say it's here? Why couldn't I say the axis of rotation is at the center of mass? And if it's at the center of mass, well then this force, the force of gravity, would have no torque, and the torque from F1 would just have to balance the torque from F2. But once again, I could pick, what about this axis point at F1? Well, if this is the axis of rotation, well then this force has no torque, and the torque due to gravity is actually going to go in the clockwise direction now, and it must balance the torque from force 2. So what we're seeing here is that there are numerous options, and that around all of these points, the torque, or the net torque, must be zero, because if not, the object would start to rotate. And so, in fact, for an object with zero angular acceleration, in other words, it is not speeding up, slowing down its rotation rate, it's not starting if it's currently stopped, the net torque about every point on the object must be balanced. And the reason why this is the case, because if it was not, well, if it wasn't balanced, then it would start to rotate. And this tells us something very interesting, that we can pick any point on this object to act as the axis of rotation, and the net torque could be zero. And so if we're going to do that, let's pick positions where the torques are going to be as simple as possible to make our lives as simple as possible. So let's kind of look at an example to see how exactly we could utilize this. So let's say we have a 2-meter long board with a mass of 4 kilograms, and it's placed on 2 cinder blocks, one on each end as we see here, and there's 2 bricks with a total mass of 8 kilograms placed on the far right end. And so we want to determine the force of each block on the board. Now, if the bricks weren't there, we could probably say, oh, okay, there's going to be 40 newtons of force down from the board, so there should be 40 newtons up on both sides. But these bricks are complicating things because we have more force going down on the right end, so the block on that side is going to have to push up more to compensate. So this looks like it could be a little complicated. So let's kind of run through the strategy that we should employ whenever we see a situation like this. Well, first, let's go ahead and draw an FBD. But the thing is, though, is that typically we've drawn FBDs as dots. We've said all of the mass is located at that dot, and we apply all of our arrows or our force vectors. But the thing is, though, is that now that we have torques that we're going to have to look at, where those torques are, and so in other words, where those forces are positioned, actually matters. So we're going to draw the object. I think it'd be simplistic, but we're going to actually draw its dimensions. So I'm going to draw my 2-meter long board here, and I'm going to go ahead and write down all my forces. I have a force due to gravity at the center of mass of 40 newtons. I have F1 and F2 from the two different cinder blocks. I don't know what those values are. That's what I'm looking for. And additionally, the bricks are going to be pushing down with 80 newtons of force on the right end because that's how much gravity is pulling them down. So for them to remain motionless, they must be pushing on the board with 80 newtons of force. All right, so we've done that first. Now, let's go ahead and write a net force equation. And our net force equations, if I look here, okay, well, I've got F1, Fg, F2, and Fb. All of those together must equal 0 because this board is not accelerating around. But I only know 2 of these forces, and I have no way of determining what the other 2 are just based on this information. So let's take it a step further. Let's go ahead and start writing a net torque equation, but to do that, I need to pick an axis of rotation for my torques to be positioned around. But I get to pick that point, so let's pick the one that's going to be as simple as possible. Well, I'm actually going to pick the right side of the board, that far right position, because if we do this, we've automatically eliminated the torque from F2 and the force from the bricks because they are acting on that axis, so I don't need to worry about them. So now I only have 2 torques that have to be balanced. The torque from F1 and the torque from the force due to gravity, they must be balanced. So let me go ahead and start sticking some stuff in. So I'm going to say R1 times F1 plus RG times FG is equal to 0. And you notice I'm going to put a negative here for F1. And the reason why I'm doing that is that F1 would cause it to go in a clockwise direction or a negative direction, and FG would cause it to go in a counterclockwise direction or a positive direction. And now let's go ahead and stick some values in. So we're going to have 2 meters times negative F1 plus 1 meter, and it is 1 meter for Fg because it's at the center of mass, times 40 newtons equals 0. So this will be 40 and move to the other side, get negative 40, divide by negative 2, and we get that F1 is equal to 20, typo here, that should be 20 newtons, 20 newtons, not 20 meters. Well, now that I figured out F1, though, I now know 3 of the forces. So I can just use my net force equation to figure out F2. So let me go ahead and plug some values in. So F1 is 20 newtons, Fg is 40 newtons, Fb is 80 newtons. But notice I've put negative signs on both Fg and also technically on Fb because both of those are pointed down, and the other 2 forces are pointed up. So remember, when we're talking about torques, negative clockwise, positive counterclockwise. When we're talking about forces, typically we're going to do positive up, negative down. So you just have to make sure we separate those. And now if I solve for F2, I'm going to get a force of 100 newtons, which makes sense. I would expect this force to be bigger than F1, and additionally to be bigger than the force from the bricks because it's also having to support the board. So at this point, though, we've got these values, and we might be okay, we're done, but maybe we're not 100% sure we did every single detail correctly. So now we're actually going to double check that we did this right. And how I'm going to do that is I'm actually going to just pick another net torque equation by moving my axis of rotation. So I'm going to not worry about this axis anymore. Let's say the axis of rotation is in fact on the left side of the board. And if that is the case, well then there's no torque from F1, but the torque from Fg, F2, and Fb must be balanced. And looking at these, F2 would be positive and Fg and Fb would be negative. So I go ahead and stick in my numbers. I'm going to have 1 times negative 40 for Fg plus 2 times 100 newtons positive for F2 and 2 times negative 80 for Fb equals 0. And if we do that, we get negative 40 plus 200 minus 160. That does equal 0. So you know what? I am 100% positive I have done this correctly. So the forces on this board are F1 is 20 newtons and F2 is 100 newtons. So let's look at one last thing together. Let's say we have a bar with an axis of rotation, like an axle or something, through its center. And if we were to look at the forces on this bar, well, there would be two forces. One would be the force of gravity that's applied, and we know this now, at the center of mass of the object, which would be on that axis point. And additionally, the normal force would come from the axle pushing up, so that would also be on the axis point. So the forces are balanced because those are going to be equal and opposite, but additionally, the torques are balanced because really there's no torque here. Each of these forces have torques that would be applied on the axis of rotation, so there is no torque here. But let's say we were to move that axle to a different position. Let's say the axle was instead at the top. And if it was at the top, and if I look at these forces, well, I've got Fg once again going from the center of mass and Fn going from the axle, and those forces are balanced. But why are the torques balanced? Well, there's no torque from the normal force because it is at this axis. And additionally, though, there's no torque from the force due to gravity, because the force due to gravity is pointed down, which is the parallel to this lever arm. So there's no perpendicular force. This object is going to just stay here. It's not going to start rotating one way or the other. Okay, well, let's look at one more slightly different situation. What happens if we had this right through the center at the bottom? Well, if we had it perfectly straight up and down, it would remain standing in this vertical position. It wouldn't tilt down, it would just stay like this because, once again, the force due to gravity will be parallel to the lever arm, and therefore there is no torque on this object. But this is kind of a bizarre situation here, because what we're saying is, at this perfect position, this object is balanced. And in fact, we're going to see that that's the case on all of these. So this one here we know is balanced for sure because the force due to gravity is on the axis. But if we look at this one, let's say you were to tip it one way or the other, well, gravity would just pull it back to this balanced position where the force due to gravity would be parallel to the lever arm. And on this one, though, rather than going back to the position it's in, if you were to barely tilt this one way or the other, it would swing down until it was basically in the second position. So if you tilt it just a little bit, it would become unbalanced and seek out this bottom equilibrium position. But this is very, very crucial here, is that a balanced object is an object where the center of mass is vertically in line with whatever our pivot point or axis of rotation that we're considering. So for all three of these objects, they are currently balanced because their center of mass is vertically in line with the pivot point, and therefore the force due to gravity is parallel to the lever arm, and there's therefore no torque on the object. But as soon as we start to move that even so slightly off of that being vertically in line, well, now there's a net torque, and it's going to cause it to become unbalanced and go to this new balanced point. Okay, so what are our main takeaways for this fairly short lesson on rotational equilibrium? Well, one, can we explain what conditions need to be satisfied for an object to truly be in equilibrium? One, that there needs to be no net force, but also that there needs to be no net torque on any point on the object. Can we explain why the net torque around every point must be zero for an object in rotational equilibrium? Can we solve problems utilizing zero net force and zero net torque equations, keeping in mind that we can pick our axis of rotation and the net torque will always be zero around that point, and we should pick it to make our lives as simple as possible. And lastly, can we explain how an object can remain balanced, keeping in mind that the axis of rotation and the center of mass must be vertically in line with each other so that that force due to gravity is parallel to the lever arm, and therefore there's no torque due to gravity.